Okay, so far we've looked at how to construct Hess cycles using enthalpy combustion values to work out the enthalpy change of a reaction. And we showed you how to construct these cycles from scratch rather than just telling you to draw the arrows pointing down towards the product combustion, which is what most textbooks would tell you. And then the second method they show you in textbooks is what happens if you given enthalpy formation values and they tell you to draw a cycle with the arrows pointing the other way, away from the elements. So if you just learn these two methods to just follow and do questions, then you'd be stuck when you haven't got a question which is just giving you enthalpy combustion or just giving you enthalpy formation or not even giving you either of these. Okay, so here's an example. So this is an actual exam question, and you've got to work out the enthalpy of a reaction, and you're given some data, and you're given a mixture of enthalpy formation values and combustion value. There's an enthalpy combustion value here. So if you only just follow the method here, where you either just give enthalpy combustion values and you follow this method to construct a cycle pointing arrows down towards the product combustion, or you use this method where you're given just enthalpy formation values and you draw the elements down here pointing arrows upwards, and you did that without thinking about why the arrows go where they are, then when you get confronted with questions like that, you're going to be lost. So this is why I'm showing you why the arrows point where they do. So that's what we're going to do today. We're going to show you how to construct Hess cycles using enthalpy formation values, and rather than just telling you, okay, just draw the cycle like this and point arrows upwards and not think about it. Okay, so think about why the arrows go where they go in order to be able to do questions which are not straightforward. So here's a question where we've got given some enthalpy formation values rather than enthalpy combustion values, and we've got to work out using these values the enthalpy change for this reaction, which is a decomposition reaction. So when we heat lithium carbonate, it decomposes to give us lithium oxide and carbon dioxide. So what I'm going to do is I'm going to write the equations out to represent enthalpy formation of these substances and put the values on the arrows. And then we're going to use those equations with the equation I want to work out the enthalpy change for to construct a Hess cycle. So the enthalpy formation of a substance is forming the substance from its elements. So the enthalpy formation of lithium carbonate will be written as follows. So the lithium and carbon and oxygen are the elements that form the lithium carbonate. And that value is minus 1216. And we balance for 1 mole of the lithium carbonate. And we can even put the state symbols. So I can do the same for the other substances we're given. So the formation of lithium oxide is from its elements, which are lithium and oxygen. And we can put the state symbols as well. And balance for 1 mole of lithium oxide. And the value for this is minus 596. And we can do the same for the formation of carbon dioxide from its elements. And the value for this enthalpy change is minus 394. So I'm going to use these equations in combination with the equation I want to work out enthalpy change for to construct a Hess cycle. So I'm going to copy this equation. So this is the one I want to work out enthalpy change for. So I'm going to try to find in these equations the species and use those equations to link the reactant side to the product side through an alternative route. So I can see with lithium carbonate, I can find here, lithium carbonate appears here. So I take that equation and link it with the lithium carbonate there. I do the same for the other substances in my equation. So lithium oxide, I can see it's here, so maybe highlight that. And I'm going to move that equation and link the lithium carbonate there. And then finally, carbon dioxide is here, which I can see here. So maybe use a different colour there and link those. So what you notice now, on this side of these arrows, I have the elements that form these substances. So I've got lithium, I have carbon, I have oxygen. So I'm going to just group these elements into a box. So I'm just going to get rid of this and put these elements into a box. So they were lithium, carbon and oxygen. I can leave it as that. I can even write elements in words. If I really want to be thorough, I can balance this equation. So we can see there's 2 lithiums on this side and 2 lithiums on this side. So there should be 2 lithiums here. I can see that there's 1 carbon this side and 1 carbon this side. So there's only 1 carbon. I can see there's 3 oxygens on this side and there's also 3 oxygens on this side. So I can put 1.5 here to balance both sides of the equation. So what I'm going to do next, I'm just going to tidy this bit up because I've already got these species in the equations here. So I'm just going to rub these out and then I'm just going to push these arrows up like there. And I could tilt these arrows like I've done before with the reactant side tilting from top left to bottom right and the product side tilt from top right to bottom left to complete my cycle. So applying Hess's law, the enthalpy change for this reaction is independent of the route taken. So I could take this route. So I'm going to draw my alternative route from there to there. So if I use the rules I did from my last video, every time I travel against the flow of the arrow, I switch the sign. Every time I travel with the flow of the arrow, I keep the sign. So I'm going to do that and do the calculation. So enthalpy change is going to be, so against the flow of the arrow, so it's minus 1216. And I don't have to multiply a factor for this value because there's only one of these. In fact, all of these are only 1. So I don't need to multiply any of these values. So I've travelled along this route against that flow of the arrow. So to finish my journey, I'm going to go with the flow of these arrows. So that's going to be plus minus 596 plus minus 394. So minus and minus is a plus. Plus and minus is a minus. Plus and minus is a minus. So putting the numbers into the calculator, I get plus 226 kilojoules per mole. And this makes sense because this is a thermal decomposition, which means I need to put heat into the lithium carbonate to cause it to break down. So this matches the fact this is endothermic. I'm putting energy into causing the decomposition. So let's look at the second example where we want to calculate the enthalpy of hydrogenation of ethene, and we give enthalpy formation data again. So the first thing we're going to do is write the equation for the reaction we want to work out the enthalpy change for, which is the hydrogenation of ethene. So we start with ethene. We're going to add hydrogen. We're going to get ethane as the product. So this is the enthalpy change I want to work out for, which is a hydrogenation reaction. So then I'm going to write the equations to represent enthalpy formation of ethene, enthalpy formation of ethane. So enthalpy formation of ethene will be written as follows. So we're forming 1 mole of ethene from its elements, which are carbon and hydrogen. We can put state symbols in. And we balance for 1 mole of ethene. So that's the equation that represents enthalpy formation of ethene. So we know the value for this enthalpy formation is 52.2. So we can write the equation for the enthalpy formation of ethane. So that's forming 1 mole of ethane from its elements, which are carbon and hydrogen again. And we balance for 1 mole of ethane. We put the state symbols in. And we know the value for this enthalpy change is minus 84.7. So what I'm going to do, as before, I'm going to try and find these species in my equation I want to work out the enthalpy change for from these equations and connect them to form an alternative route to this one. So I can see straight away that I've got ethene here, and so I'm going to pick up this equation and connect the ethene together there. I can see that I've got ethane here, and I'm going to connect those together. Now it looks like I've got a problem because I haven't got an equation for the hydrogen, but that isn't a problem, and I'll show you why in a bit. But before we do that, you can see that on this side of these arrows, these are the elements that form these substances. So I'm going to rewrite this and put those into a box. I could write in here the elements, carbon and hydrogen, and balance it for the equation on this side, which would be the same as the equation on that side. So that would be 2 carbons and 3 H2, because I have 2 carbons on both sides and 6 hydrogens on both sides, which is 3 lots of H2. Or I can actually save time in the exam for OCR, just write carbon and hydrogen, or even OCR will allow you to write elements. What I'm going to do next, I'm going to just tidy this up, and we don't need these here because they are already up here, so I'm going to rub those out. I'm going to move the box up there, and again I can tilt these arrows from top left to bottom right for the reactant side, and bottom left to top right for the product side. So I've got this issue with no arrow for the hydrogen, and I must connect everything on the left hand side to everything on the right hand side to my alternative routes. I can't just leave that alone, but that isn't a problem if you think about it. This is hydrogen as an element, so how do I make that from elements? So hydrogen from its element, which is also hydrogen, H2, there'd be no enthalpy change. There's no change there going from H2 to H2, so this is 0. So enthalpy formation of any elements is going to be 0. So I'm going to draw my alternative route from the left hand side to the right hand side. So from the left to the right, there's my alternative route, and I'm going to apply Hess's law. So the enthalpy change of this reaction here is going to be going against the flow of this arrow. So I'm going this way around to that way. So going against the flow of this arrow, against the flow of this arrow, and then with the flow of this arrow. So against the flow is going to be minus plus 52.2, and then we have minus plus 0. Well, that's not going to make a difference, that's just going to be 0. And then we're now on this island, we're going to finish the journey. In this direction we're travelling with the flow of the arrow, so we keep the signs, we use a plus, minus 84.7. And again, we don't need to multiply any of these by any factors. It just happens that these are all 1 mole of each. If it was the case that these was 2 moles, I need to multiply this by 2 and so on. So what we're going to do is just work this calculation out. Plus and minus is a minus 52.2. Minus 0 makes no difference, so I'm going to ignore that. Plus and minus again is a minus, so that's going to be minus 84.7. Putting the numbers into the calculator give us a value of minus 136.9 kilojoules per mole. So hydrogenation of ethane is going to be exothermic. So lastly, let's look at this question where we're given a combination of enthalpy formation and combustion data to work out the enthalpy changeable reaction. So the question here is asking us to work out the standard enthalpy formation of nitroglycerin using the enthalpy change data above. So what I'm going to do first is write the equation for the enthalpy of formation of nitroglycerin. So I've written now the equation that I want to work out enthalpy change for, which is the enthalpy formation of nitroglycerin. Now I've written it to balance for 1 mole of nitroglycerin as in the definition of enthalpy of formation. So what we're going to do is we're going to look at how we can construct a cycle to connect this side to this side. Now there's a couple ways of doing this, and the quickest way, if you look carefully in this question, is that although these values here are enthalpy formation values of nitrogen dioxide, of carbon dioxide, and also of steam, we can also think of these equations as combustion equations. So this is the combustion of 1 mole of hydrogen. So this value here is also the same as the enthalpy combustion of hydrogen. This equation shows enthalpy combustion of carbon because we're burning 1 mole of carbon. So this value is the same as the enthalpy combustion of carbon. This value here is the enthalpy of combustion of half a mole of nitrogen. So if I double this value, this will give us the value for enthalpy combustion of nitrogen, because by definition enthalpy combustion is burning 1 mole of the substance. And so I need to double this equation to show the burning of 1 mole of nitrogen. If I double the equation, the value of this will double. So MP combustion of nitrogen will be double that, which would be 68 kilojoules per mole. So effectively, I can change all these to MP combustions, and this would be plus 68, and we get rid of that half, and we need to double up here. And all I'm going to do is construct a cycle here where we're burning these substances, because we got values of those. We've got combustion value for that here. We've got combustion value of the carbon. We've got combustion value for the hydrogen, and we've got combustion value for the nitrogen here. We haven't got combustion value of oxygen, but we mentioned earlier that you can't burn oxygen, so the enthalpy of combustion of oxygen is always going to be 0. So that's one way to go about it. So that's what we're going to do. So I must draw the cycle in the exam to get all the marks. So I'm going to draw the product's combustion underneath these substances, and I'm going to draw arrows pointing towards the product's combustion, because when I burn these things here, I produce the products of combustion, so whether it's carbon dioxide, steam, or nitrogen dioxide. So I'm going to draw the arrows from these to the product's combustion. So I'm going to put the values in from the table above. So those are my values. I'm going to use Hess's law to travel from the left to the right of the equation. So I'm going to travel with the flow of the arrows here and against the flow of the arrow here. So with the flow of the arrow here, I've got a plus. With the flow of the arrow here, I've got a plus. With the flow of the arrow, I have a plus. So here I've left out the 0 in the equation because 4.5 times 0 is 0. It makes no difference. So travelling against the flow of the arrow now, I've got a minus, so minus the minus. So this works out to be minus 1182, and this part works out to be minus 605. This works out to be plus 102, and that works out to be plus 1540. And putting all the numbers into the calculator gives us a final answer, 145 kilojoules per mole. So the answer here is 145 kilojoules per mole, and that's what was on the mark scheme for the exam. So understanding how Hess cycles can be constructed and why the arrows point where they go, you could construct a bit more complicated Hess cycles, something like this. So here I've got a cycle where I could potentially work out the MP formation of ethanol from its elements, which we can't do experimentally, but we can use a Hess cycle to work this out by using experimental values. So I could find the MP of reaction of glucose to form ethanol and carbon dioxide, which is fermentation, experimentally. I could find the MP of combustion of glucose to form carbon dioxide and water, so we know this value as well. I could find the MP combustion of carbon and hydrogen experimentally to give us carbon dioxide and water, which give us the value of this arrow, so that would be the combination of MP combustion of carbon and MP combustion of hydrogen multiplied by 6 each. I could work out this value here, which is MP formation of carbon dioxide from its elements, which is carbon and oxygen. So that is really the same as the MP combustion of carbon multiplied by 6. So understanding why the arrows point where they do, I can construct more complicated cycles like this, and knowing these values experimentally, I can work out this unknown. And you wouldn't have been able to do this if you just learn the method from a textbook, which is just to learn the arrows point downwards towards the product's combustion if you're given MP combustion values, and arrows point upwards from the elements if you're given MP formation values. So this is why it was important to understand how to construct these cycles to help you do more complicated questions. So in the last 2 videos, we covered this section of the enthalpy changes topic. We know how to construct Hess cycles using enthalpy change values given to us in tables. We can use those cycles to do some calculations, and also because we can construct cycles from scratch rather than just learning a method, we can deal with unfamiliar cycles as well, hopefully.